Hey there, we're going to look at an important theorem in calculus called the intermediate value theorem. It's often introduced in like an algebra class to begin with, but we're going to look at the calculus version, which involves continuity. And so the intermediate value theorem is going to have a hypothesis and a conclusion. We'll really talk about what those two things are to better understand an if-then statement. And then we'll do a couple basic proofs using the theorem. Again, all of this is based in continuity in calculus. So the first thing we'll do is we'll state the theorem, which you'll need to know. The theorem says if f is continuous on the closed interval from a to b, this is a closed interval because both endpoints are included, then for any n value between the outputs of the function at both endpoints, f of a and f of b, so you can pick any n between the two outputs, there is a c. Sometimes we'll say there exists a c that is an element of the open interval from a to b. This is an open interval because we don't include the endpoints. So for any n between the two outputs, we can find some c between a and b such that the function will output n at that c. So such that f of c equals n. All right, so let's break this down here. First thing I want to do is identify the hypothesis and the conclusion. So the hypothesis of a theorem are the things that you assume to be true before you can make a conclusion. I've written this theorem in such a way that it's an if-then statement. So the if portion, if f is continuous on this closed interval, that's the assumption we make in order to use the theorem. So that is our hypothesis. We need a continuous function on a closed interval. Then we have a conclusion. So the conclusion of a theorem is what you can gather if the assumptions are met. And in an if-then statement, the conclusion is everything that follows the then. So this says any n value between f of a and f of b, we can find a c in the open interval such that f of c equals n. Now let's draw a picture to understand the theorem a little better. So the first thing we need is a continuous function, which I'll draw in the first quadrant, let's say. Keep things simple. I need a continuous function on the closed interval from a to b. So we have a and b, and I need a continuous function. So continuous function at the endpoints means it's got to be a closed circle. And then continuous between a and b just means it's a continuous graph with no breaks or discontinuities, okay? So maybe something like this. This might be the f function, the y equals f of x function. So we have a continuous function on the closed interval from a to b. So we've met our hypothesis. The conclusion is then that for any n between f of a and f of b, well, f of a is right here. This is the output when we input a, and f of b, so f of a is right there. That y value, that output, f of b is this output here, this y value. The theorem says then, okay, if you pick an n value anywhere between f of a and f of b, so we're going to pick n, we're going to pick an n here, any n you want. Any y value. You could pick this to be n, this to be n, this to be n, as long as it's not f of a or f of b, and it's between them, not outside. So we could pick any of those n values. The theorem guarantees that there is a c between A and B. So there exists a C that lives here between A and B, such that f of C equals n. So let's do this in a couple different ways. We'll use blue here. So let's say we pick this n value right here. I can pick any n that I want. The theorem says I should be able to find a C between A and B such that if I input that C value to my function, it gives me the output of the n that I chose. And we can see that that's true. F of C equals n. Let's try another n. I could pick an n down here. We'll call this n1, let's say. n2 certainly will also give us, we'll call this C1, will also give us a C, we'll call it C2, between A and B so that its output is n2. And it could also occur that you get more than one C value. Let's do another drawing here to illustrate that. A different shaped graph. Maybe you'll recognize a graph that does this kind of thing. A sine or cosine function. This function is continuous on the closed interval from A to B. And then in this case, f of A is down here, this output, this y value. F of B is right here. And we can pick any n we like between those. We should be able to find a C between A and B so that it outputs n. And in fact, if we look at this n value, we get a C value right here that's between A and B. If we keep going, we get another C value right here. If we keep going, there's yet another C value. So sometimes there are multiple C values that satisfy the conclusion of the intermediate value theorem, but the intermediate value theorem guarantees that there is at least one, there is a C. Okay, so that's the theorem. It makes perfect sense. Basically, it says if you travel from, let me use a highlighter here to show you. If you travel from f of A to f of B, you have to hit every y value between f of A and f of B. You can't miss any if you have a continuous function. But as a student, you should start picking up on the technicalities here, the notation, the language, etc. Definitely understand what it means, but also be able to state it precisely. Now let's practice applying the theorem in different ways just to really get our hands on it. Let's look at an example. Let f of x equal the square root of x plus 4. Part A, does f satisfy the hypothesis of the intermediate value theorem, which is often abbreviated IVT? Now, I prematurely wrote the question mark because I need to give you more information. Does f satisfy the hypothesis of the IVT on the interval from 1 to 5 inclusive? Well, remember the hypothesis of the intermediate value theorem just says the function has to be continuous on the closed interval. So we have to look at this function f of x equals square root of x plus 4 and find out where it's continuous. Well, this function is a square root function. It's continuous anywhere that we don't get a square root of a negative. So it's continuous on the interval from -4 to infinity, which, by the way, is the same thing as the domain of the function. So f is continuous on -4 to infinity. Since 1, 5, this closed interval from 1 to 5, is included inside -4 to infinity, the function satisfies the hypothesis. So pretty simple. If the function is continuous on the interval, it satisfies the hypothesis. Now, since it satisfies the hypothesis, we're allowed to invoke the theorem to make a conclusion. So, what does the IVT guarantee about f in this context? What does the IVT guarantee about f in this context? Okay, so what is the conclusion? Well, the conclusion states that for any n between f of a, which is f of 1, so f of 1 means plug 1 into the function, so we get the square root of 5. So any n between the square root of 5 and f of 5, which is the square root of 9, which is 3. So for any n between the square root of 5, which is 2 point something, and 3, it guarantees that there is a c that is an element of the open interval from 1 to 5, such that f of c equals the n that was chosen. Okay, so just a direct application of the intermediate value theorem, identifying the hypothesis and conclusion and applying them. Let's do another example. Let f of x equal e to the x plus 2x minus 3. And I encourage you to dig more into this. Look at the graphs of these functions. Use Desmos or something and see how they behave. See if you can understand graphically what this is saying. Part A, does the function f satisfy the IVT hypothesis on the interval from -1 to 2, the closed interval from -1 to 2? Well, f is continuous everywhere. F is continuous everywhere, so it's certainly continuous on this closed interval. So it satisfies the hypothesis. Remember, you can raise e to any power and you can multiply 2 by any number. So this function, the domain of this function is all real numbers. Therefore, it's continuous everywhere. Part B, I'm going to ask a different question. Does the IVT guarantee a root between -1 and 2? So what do we mean by a root? A root is also called a zero or an x-intercept if you're thinking graphically. Basically, it's an x value, an input that turns the whole function into 0. So let's investigate. Let's look at what the IVT does guarantee, and then we'll try to answer the question. It guarantees that for any n between f of -1, f of -1, it looks like, is approximately -4.63, okay? For any n between that approximate value and f of 2, which is approximately 8.39, for any n between those two outputs, can you fill in the blanks here? There is a what? There is a c along the x-axis in the open interval from -1 to 2, so c is between -1 and 2, such that f of c equals the n that we chose. Okay, so how can we use this to answer the question? Well, in this case, we want a root which means we need to output 0. So can we choose an output of 0 and get a conclusion here? And the answer is yes, we can. Since 0, I'll just put in parentheses, this is like our n value. Since the n value of 0 is between f of -1, which is negative, by the way, so it's less than 0, and f of 2, which is greater than 0, positive. 0 is between that negative and positive number, so since 0 is between those, there is a c between -1 and 2 such that f of c equals 0. You can pick any n you want between f of -1 and f of 2, and this will be true. In this particular case, we're picking 0 because we're looking for a root. So the answer is yes, there is a root between -1 and 2. Okay. I hope that makes sense. Okay, we'll wrap up here. We're hitting like 16 minutes, so we'll wrap up with a proof using the intermediate value theorem. Use the IVT to prove that the equation not function, but equation, has a solution in the open interval from 1 to 2. And the equation looks like this. X plus sine x equals x squared. We want to prove that this equation has a solution. Now, I want to step back for a second. Look at this as an algebra problem. If I just told you to solve this equation, that would be tough. This is not a common type of equation that we learn how to solve in an algebra class. But you can use calculus techniques to help solve difficult equations, or approximately solve, or find out maybe if they have solutions. So here, we're going to prove that there is a solution between 1 and 2 without doing anything very fancy at all, even though this equation is difficult to actually solve. So how do we do this? So anytime you do a proof, you start with the word proof as an indicator that you're beginning, and then when you finish, use the end of proof symbol. Some people call it a tombstone to show that you're done. So you need to start your proof and end your proof, and then in between, provide your proof. So here we go. If we're going to use the intermediate value theorem, we need a function. So the first thing we have to do is define a function. What I'm going to do is I'm going to rethink my equation. This is a really common way to do it. I'm going to get 0 on one side. So I'm going to subtract my x squared over. Okay? And then this is what we're going to use as our function. So the first thing I'm going to do in my proof is let f of x equal x plus sine x minus x squared. Now the next thing we need in order to invoke the theorem is we need our function to be continuous on a closed interval. Well, I have an open interval here, so I might as well just use that as my closed interval. So what I need is for this function to be continuous on that closed interval. So I need to first figure out where this function is continuous. So I'll use the words note that f is continuous everywhere. So it's continuous from -infinity to infinity. You know, these x, sine of x, and x squared don't have any domain restrictions, so it's continuous everywhere. So it is certainly continuous. You know, I want to define a closed interval that's relevant to the problem. If it's continuous everywhere, then it's also certainly continuous on the closed interval from 1 to 2. Okay, now we're getting somewhere. We've satisfied the hypothesis of the IVT with a function. Now all we have to do is follow the blueprint. Just state the conclusion and see where it leads us. When you want to invoke a theorem to make a conclusion, you should cite the theorem. So I'll say, by the IVT, for any n, you can see why you need to know the theorem, right? For any n between f of 1, which is, approximately 0.84147, we'll stop there. For any n between f of 1 equals 0.84147 and f of 2, which is approximately negative 2.09070. When you're trying this yourself, make sure your calculator's in radians mode since you're taking the sine of your x values. Okay, so the theorem says for any n between those two outputs, there is a c. Where does c come from? C is from the open interval, so it's strictly between 1 and 2, such that f of c equals that n. Okay? So here we go. Here is our f of x. We want it to equal 0. So that's going to tell us that we're going to choose this number over here. That's why we've got 0 over here. It's really common to do that. We're going to use this as n. Okay? Now, it says for any n between 0.84 and negative 2.09, we can apply the theorem. Luckily for us, 0 is between 0.84 and negative 2.09. So we can say since 0 is between f of 1 and f of 2, we don't have to restate their values. We've already got them written. There is a c in the open interval from 1 to 2, such that f of c equals 0. 0 is a particular n value for which this is true. So f of c is 0. But now, let's look at what that means. F of c equals 0. Well, that means f of c, here's our definition of f. F of c means we plug c into this function for x. So in other words, we know that c plus sine of c minus c squared equals 0. Now we want to back up and make it look like this. So I'll add the c squared back to the right side. So we know that c plus sine of c equals c squared. What is that telling us? That means that c is a solution to the equation. So c is a solution, again, often called a root as well, to the equation. And what are we trying to prove? We're trying to prove that the equation has a solution. So we just did. But even more so, we need that solution to be between 1 and 2. We already know that c is between 1 and 2. It was part of the theorem. So c is a solution to the equation, and c is in the interval from 1 to 2. Therefore, we've proven the statement. We are done with our proof. Now, I hope the logic here makes sense. I didn't really include any extra words or anything. This is about as concise as I could think to make it. You can use language that's different, but your notation and your logic has to be sound, and it has to follow the theorem. So I hope that makes sense. Of course, you probably need some practice with this. Usually Calculus 1 students haven't had a lot of experience with proofs, but if-then type proofs are usually rather straightforward and a great place to start. So learn the IVT, do some practice, and I hope you enjoy it.